Okay, good morning, everyone. Welcome to the second morning session of AJG in solids. So the first speaker is Manish. He will talk about Attosecond metrology of phase-coherent multi-PHz current in bulk solid. Thank you for your attention. Please, Manish.
Thank you, Marcelo, and I'm also thankful to other organizers for this opportunity to present this work. So in the next half an hour or so, I'm going to show you how one can generate and measure phase-coherent multi-PHz currents in bulk solids. And these currents are generated when one shoots bulk solids with ultra-short intense laser pulses. And or this can also be generated in ultra-thin nanofilms. So before I go to show you the temporal characteristics of this multi-PHz currents, so first we have to look a bit into the spectral domain. So this is the easiest thing that an experimentalist will do, to look into the spectrum that actually emanates out of a bulk solid when it is shot with intense laser pulse. So the first signature of this kind of interaction is the formation of high harmonics from bulk solids. And this work, this whole area field actually started with the work of GEFES from Stanford, where they shot ultra-short intense mid-infrared pulses into zinc oxide crystal, which has a band gap of around 3 eV. And they saw high harmonics for the first time beyond the perturbative regime. So they measured high harmonics to the order of 21st or the 19th harmonic order. So they went all the way from the mid-infrared range to the UV range. And then came the work from the group of Professor Rupert Huber, where they shot intense terahertz pulses into gallium selenide crystal, and they reported formation of high harmonics all the way from the terahertz domain to the visible domain. And then came our work in 2015, where we shot thin films of silicon dioxide, which have a band gap of around 9 eV with intense optical pulses, and we reported high harmonics all the way from the visible domain to the XUV domain. And this energy range is also the same energy range where isolated attosecond pulses are routinely generated by high harmonics in gases. So once you shoot optical pulses into dielectric medium, there is a formation of carriers. So there is a formation of holes in the valence band and the electrons in the conduction band. And then there are two different kinds of mechanisms which can lead to high harmonics in solids. The first mechanism, and this is the mechanism that we also proposed in our work, is that the electrons are generated in the conduction band, the first conduction band of fused silica, and these are accelerated by the laser pulses, and by acceleration of these carriers and by the nonlinearity which is coming from the dispersive profile of the conduction band, there is emission of high harmonics. And this is the non-recollisional dynamics. And then there is, of course, another possibility that you can have recollisional dynamics. So you create carriers in the two bands, the electrons and holes in the conduction and the valence band, and these are accelerated in presence of the laser pulse. And after a while, they recombine and they lead into high harmonics. And this is the mechanism which was suggested by GEFES and also a bit by Schubert. And this is the recollisional dynamics. And this is similar to the three-step model that Qualcomm has proposed for explaining high harmonics in gases. Now in our experiment, we have shot intense single cycle pulses into thin films of silicon dioxide. And this was first done with amorphous sample, but later on it was also done in crystalline sample, and no differences were observed. And we record the high harmonics as a function of increasing field strength, or as you can see here. And what we see is actually there is scaling of the spectral scaling of the of the cutoff, and also there is a scaling of the intensity of these high harmonics. And if you look into how the cutoff energy scales with electric field, we found that the scaling of cutoff energy with respect to the field is linear. And this is in contrast to quadratic scaling of the cutoff energy with respect to field that is observed in high harmonics from gases. Now, as I told you, we were able to explain this high harmonics only from dynamics of electrons in the first conduction band of SiO2. So here you look into the first conduction of band of SiO2 in the gamma m direction of the below zone. So the other two directions, the gamma A and the gamma K direction, are a bit less nonlinear, so they don't lead to very high energies in the spectral domain. And now if you look into this particular band, and this band can be decomposed into a series of special harmonics in the reciprocal space. So you can have the decompose into a cos k band, 2k, and so on. So cos k implies there is an interaction of only two distant neighbors which lead to formation of this band. And if you go on further, so like cos 6k band is actually formed when there is an interaction of six distant neighbors in the real space, and this leads to a contribution of the six distant neighbors in this dispersion profile of the band. And now if you look into how if you solve the semi-classical equation and look into what is the spectrum that you get from the cosine K band, you will see that the spectrum has a lower cutoff energy compared to the higher special harmonic bands. And so the thing is actually with the cos K band, which is much less nonlinear compared to a cos 6K band. And this was also sufficient to explain the linear cutoff scaling that we observed in our experiment. And now if you consider the fact that the SiO2 has a lattice constant of around 5 angstrom, and the peak field that we apply in our experiment is around 1 volt per angstrom. So the cutoff energy that you would expect from a simple estimation is only 5 eV. And this is much less compared to the 35 eV cutoff that we see in our experiment. So what it implies is actually there is an effective lattice constant which the system, which our laser pulse is interacting in the system. And with our observed estimation of the cutoff, we were able to claim that we see interaction of up to a sixth distant neighbor in the conduction band of SiO2. So from this particular work, we had the information that the high harmonics from solids actually has the information of dispersion profile of the electronic bands in solids. Now, if you look a bit more carefully, how the spectral intensity of individual harmonics in our experiment actually scale as a function of the field strength, and this can be seen by this equation over here. And now if you look into only the 11th harmonic order in our experiment and look into how this scales as a function of the field strength, we were able to explain this intensity scaling only by considering the 5th special harmonic in the conduction band. So this was only explained by the cos 5Ka in this expression over here. And if you look into the 15th harmonic order, we could explain this intensity scaling only by the 6th special harmonic contribution in the first conduction band of SiO2. And now if you look into the ratio between this spectral scaling over here and this scaling over here, we were able to estimate what is the contribution of the 5th spatial harmonic, that is cos 5K with respect to cos 6K in the conduction band, and we were able to get this ratio, and this was quite compatible with our estimation. And what does it mean? So it means actually that so in principle, of course, all these parameters can be retrieved by angle-resolved photoemission spectroscopy, but angle-resolved photoemission spectroscopy does not work very good for non-conducting solids like wide-bandgap dielectrics and semiconductors. And here, of course, retrieving such quantities is a big challenge in other experiments. So from this experiment, for the first time, we were able to claim that we can retrieve very fine features of the electronic bands of solids. And if you look into the resolution that we have in this experiment is of this order, and this is quite reasonable with respect to the modern RPS experiments. Now, in the recent work from the group of Professor Gulil-Marquez, so what they have done is actually they have incorporated this into the real space, and they have been able to reconstruct the real space valence electron potential of bulk solids by looking into high harmonic generation. And all these things that I just showed you was done in reciprocal space. But if you're interested, how does it manifest in the real space, you can look into this new publication from his group. Now we will go back to the temporal characteristics of these currents that you induce in the solids. So when you shoot intense optical pulses into SiO2, for example, so you generate carriers, so you generate holes in the valence band and electrons in the conduction band, and these electrons and holes are dipole coupled to each other, and this dipole coupling leads to interband polarization. And if you look at the same time of this interband polarization, there is of course the motion of carriers in the individual bands, and this leads to intraband contribution or the intraband current. And now if you look into solve this semiconductor block equations for all of these bands over here, you get a spectrum that is also coming from the interband contribution and from the intraband contribution. And you will see a spectrum of this kind. So if you see carefully, the spectrum looks more or less similar. So just by looking at the spectrum, it is very hard to say what is the mechanism which is underlying the formation of high harmonics from solids. And that's why we have to look a bit more carefully into the temporal feature. And if you do a time frequency analysis of these individual currents over here, so if you do a time frequency analysis for the interband polarization, you will see a feature like this one. So the red curve over here is the peak of the electric field of the driving pulse. And you see here the time frequency analysis is shifted towards the positive side, which implies it has a positive chirp. And which means actually the harmonics actually develop over time. And so this is similar to the three-step model. And if you look into the time frequency analysis for the intraband contribution, you will see that all the high harmonics are released all at once. So this is a concurrent emission of high harmonics. And also the synchronization of the harmonic emission with respect to the peak of the field. So here you see they are offset with respect to the field in case of interband contribution. However, in the case of intraband contribution, it is perfectly synchronous to the field. Now, so the way we have performed our experiment is by doing attosecond restreaking of the EUV emission that we have in our experiment. So we shoot intense optical pulses, and you generate UV emission and the optical. They both co-propagate together, and these are separated with respect by spectral filtering and spatial filtering, and they are focused into a gas jet, which is placed under a time of flight spectrometer, and you generate electrons by single photon ionization over here. And these electrons which are generated by EUV pulses are streaked by the optical pulses, and here the intensity of the optical pulse is low enough so that it does not cause a nonlinear interaction. And we get a streaking spectrogram which looks like this one. And this streaking spectrogram can be reconstructed by principal component generalized projection algorithm. And this gives both the information of the driving electric field and also the information of the EUV pulse. But of course, the information that you don't get from this experiment is what is the relative timing of the EUV pulse with respect to the driving pulse. And this can be obtained by doing a high order nonlinear autocorrelation of our dual mirror setup that you see over here. And this is the precise delay calibration that one can do. And by this, actually, we perfectly know what is the relative timing of the EUV pulse with respect to the optical pulse. And here in this experiment, we found that is perfectly synchronous. And if you do this experiment by replacing SiO2 film with the gas source, you will see that it has a slight offset with respect to the peak of the field, as is expected from high harmonics from gases. Now, if you look a bit more carefully into the time frequency analysis of the pulse that we retrieve in our experiment, as you can clearly see, it resembles more the intraband contribution. So they look almost similar. But we can look a bit more carefully by looking into the group delay of this emission. So now if you look into the group delay, so that is how at which point in time different photon energies of EUV pulses are emitted, you will see for the interband contribution, the group delay linearly increases. So the lower photon energies are emitted earlier and the higher photon energies come later in time. However, in case of intraband contribution, so since it's a concurrent emission, so all the photons, they will be released at once. And if you look at the intraband contribution only from a semi-classical model, so in the semi-classical model, we don't consider the excitation process. We consider that the electronic wave packet pre-exists in the conduction band of SiO2, and this is just accelerated by our driving pulses. Even in this model, you can see that it has quite an agreement with our experiment. And this is the experimental group delay that we obtain, and this resembles perfectly well with the intraband current. And now, in order to be 100% sure that we are measuring precise quantities, we have to look into the things which are precisely known in literature. So if you look into the UV emission which comes from gases and characterized in our setup, we clearly see the positive chirp that is coming in case of high harmonics from gases, and this is also compatible with the semi-classical model from Levenstein. Now, if you look into how one can control this currents temporarily by shaping the driving optical pulse. As you may know, from standard gas high harmonics, there is extreme nonlinearity which is present in the generation process. So if you generate high harmonics with the cosine-like pulse, that is a CP0 of our driving pulse, and a sine-like pulse, which is pi by 2, you will see that in a sine-like pulse, you generate a double burst. And this is because of the fact that there is a extreme nonlinearity which plays a role in that kind of high harmonics. But in case of high harmonics from solids, this kind of nonlinearity is not present. So if you generate EUV emission from cosine-like pulse, that is the CP0 over here, and the sine-like pulse is CP pi by 2, you will still generate an isolated burst of emission. And this is a very important observation, which is saying that the emission process is completely different in compared to gases. And if you look here, by just changing the CP of our pulses, we are able to tune the central frequency and also tune a bit the temporal structure of our pulses. And if you generate these high harmonics with longer optical pulses, so we go a bit lower in cutoff energy. And here the important feature is actually you can go to a bit lower energy electron EUV pulses, and this is very important because most of the attosecond experiments, they suffer from the fact there is extreme temporal resolution, but the spectral resolution is really bad. But in this such kind of pulses, they are confined in attosecond time scales and they have huge spectral resolution. Now, if you look what our semiconductor block equation model tells us, so this is actually our experimental pulse. And if you solve the semiconductor block equation and look into the interband and intraband contribution, so you will see that in the intraband contribution, you will still generate an isolated attosecond pulse for both CPs of the driving laser pulse. However, in case of the interband contribution, you have a dual burst for a sine-like pulse compared to a single burst for a cosine-like pulse. So this experiment immediately tells us that the nonlinearity that we are talking in case of high harmonics in solids is much less compared to the high harmonics in gases. Now, before we go on to retrieve some quantities which are related to the currents that we are inducing in solids, we have to be very sure about the phase coherent of this currents that we are generating. So every laser pulse should generate an identical current in our experiment. So in other words, so all the EV emission that we are generating should be phase coherent. Now, how do we do that? Is actually we have done this by performing a photoelectron interferometry. So in this photoelectron interferometry, we look into interference of two kinds of electrons. So here the intensity of the optical pulse is strong enough so that we generate above threshold ionization electrons here below our time of flight spectrum, and the UV pulse generates electrons by single photon ionization. And this is the interference that we are looking into. And now if you look into the phase of this interference over here, so if the CP of our laser pulses is fixed, that we know for sure is fixed in our experiment, and if you look into interference fringes, which can come from this kind of interference, and if these fringes remain static in time, this implies that we have perfect stability of our UV pulses, the phase stability or the CP stability of our UV pulses. So now this is the spectrum that we measure in our experiment. So the green spectrum shows the above threshold ionization spectrum. So these are the peaks which are separated by single photon energy. So this is around 2.2 eV here. And then in the blue is actually the photoelectron spectrum that is generated by EV pulses from our solid. And then in the red, you see the interference fringes. Now, if you look a bit more carefully, you see this very fine fringes. And if you record these fringes over time in the experiment, you see that they almost do not change over time, and the CP fluctuation that you measure is extremely small. And now, if you so of course in our experiment, the CP, there is a small CP fluctuation of our driving laser pulse, and if you compare how this affects the CP of our EUV pulses just from a semi-classical model, you will see there's almost no effect. Now, in order to be sure that we are measuring real interference fringes, so one has to be able to change this interference fringes by changing some quantity in the experiment. Now, in this experiment, what we have done is actually we have changed the CP of EUV pulses by dispersing them through a gas tube which is filled with xenon atoms. And now what you do here is actually So the pressure that we put into this gas cell is actually very small, so it does not introduce any group delay to the EUV pulse, and it also does not distort the pulse. So that GDD, so the group delay dispersion, is also quite small. And for sure, this small pressures that we put over an experiment does not change the optical pulse at all. And now if we just vary the CP of our optical pulses, we see that the interference fringes move quite nicely. And this actually experiment confirms that what the interference fringes that we are measuring in our experiment are real, and we are able to control them. Now, since we know the precise timing of the EUV pulse with respect to the driving laser pulse, and we also know that these EUV pulses are phase coherent, so they do not change with time. So now we can actually look into some parameters of which are related to the current density that we are inducing with our laser pulses in the bulk solid. So for a medium which is very thin compared to the driving wavelength, so here the driving wavelength is around 600 nanometer, and the thickness of our film is around 100 nanometers. So the current density that you induce in these solids will be just proportional to the field of the EUV pulse. And since we know the EUV pulse in our experiment, and if the temporal profile we are sure, and if we calibrate the peak strength of the EUV pulse, and this can be done by precise calibration of the photon yield of EUV pulses in the experiment, we can actually retrieve what is the current density which we induce in the bulk solid, which actually gives rise to EUV emission. And this is an extremely high current density that we are inducing. And now with the precise knowledge of the driving field with respect to the EUV pulse, we can actually estimate the dynamic conductivity, and we can see that the dynamic conductivity actually changes to extremely big number in a very short amount of time. So in the beginning, when the pulse, the laser pulse is not interacting with the system is almost insulating, and when you interact with the system, then the dynamic conductivity increases by enormous factor. So this value over here is actually 18 orders of magnitude more than the static conductivity of SiO2. So basically switch from insulating state to a dynamic conducting state in a very small fraction of time. Now I would move on a bit and look into what else can we learn from this previous interferometry experiment about the phase behavior of EUV emission on the intensity of the optical pulses and the CP of the optical pulses. Now, as you know from the recollisional mechanism, that the EUV phase depends linearly on the intensity of the optical driver. And in the case of non-recollisional dynamics, the EUV phase should be independent of the intensity of the optical driver. Now, so we have performed again the same kind of interferometry experiment. The only thing is actually here we are able to replace the source which is actually emitting the EUV pulses in our experiment. So we can switch between quartz or fused silica with an argon gas cell. Now in our experiment, we have observed two different kind of interference fringes. So one, if you look carefully into this spectrum over here, which is the interference fringe of the above threshold ionization and the EUV photoelectrons, we see that there are two kinds of fringe spacing. So we see in the high energy, there is the fringe spacing is quite big, it's on the order of 2.2 eV. However, in the low energy, the fringes are much densely packed, and they have a spacing of around 0.3 eV. And this spacing should tell us something about the relative timing of ATI electrons with respect to the EUV photoelectrons. Now, since in our driving laser pulse, we know what is the synchronization of the EUV pulse with respect to the driving pulse. We know that it is perfectly synchronized in case of EUV emission from solids, and this has a tiny small offset. So this has, if you consider the EUV pulses to be released by short trajectory in case of gases, they will come a tiny bit earlier with respect to the peak of the pulse, but they are not a big offset from the peak. And we also know that the electron energy, which is bigger than the twice of the conservative energy, so we are looking into energies which are over here, and here these energies are actually generated by a rescattering process. So the electrons are generated at the peak of the pulse, and they recombine or re-scatter from the core at a bit around half cycle later. And now with this timings here, so that the EUV pulse is coming over here, then the rescatter electrons in ATI are coming over here. We were able to explain this big spacing fringes. However, for the small spacing fringes, one has to look into the direct electrons, and there are multiple bursts of direct electrons which can exist in the experiment. So we can have multiple, and if this actually interacts with an isolated burst, it can lead it to generation of dense fringes.
Sorry, you have 5 minutes left.
Okay. Now, if you look into the phase difference that we are measuring in our experiment, so this is the phase difference of the ATI electrons with respect to the phase of the EUV pulses. Now, if you fix the phase of the ATI electrons and look only at the phase of the EUV pulse, then actually the phase that we measure in our interference experiment is only sensitive to the phase of the EUV. Now, in order to do this intensity dependence, we have done exactly this. So we have fixed the intensity of the electrons, which intensity of the pulse, which is generating ATI, and we have varied only the intensity of the pulse, which is generating EUV emission. Now, we look into the spectral fringes in case of argon and how it varies actually with the intensity of the pulse. So here you see the interference fringes which are formed, and these are over energy scale over here. And these fringes, they move quite nicely with when we increase the intensity of our pulses in the experiment. However, when you look into the fringes which are formed by UV emission from quartz, they almost do not change when you increase the intensity of the pulse. And now, from this motion of these fringes in our experiment, we are actually able to estimate what is the phase actually which is changing, phase of the EV pulse which is changing as a function of increasing intensity of the pulse. So in case of quartz, and then what we can do is actually we can do a Taylor's expansion of this phase and actually look into the CP phase and the group delay dispersion phase. And if you look here, the phase of the CP is almost varying quite linearly with respect to the intensity of the pulse, and in case of quartz, it remains almost constant. And the same goes for the group delay dispersion. So here also there is a huge variation of the GDD for argon, and in case of quartz, it remains more or less static. And now if you look into how this small variation of intensity actually affects the shape of the UV pulse. So in case of, by varying only the intensity by 5%, and this is quite reasonable in the experiments, you can change the waveform of the UV pulse by quite a lot, and this remains almost static in case of quartz. Now, one can also do the UV phase dependence on the CP of the optical driver, but here, of course, we cannot independently change the phase of the UV pulse with respect to the ATI electrons, and here they both change at the same time. So what we have to do in order to estimate this phase of the UV pulse change, we have to subtract it with our phase that we measure in our experiment with the phase of the pure ATI electrons. And here again, what we see is actually there is a huge dependence in case of argon, that the phase varies quite dramatically with respect to the CP change of the optical pulse, and in case of quartz, it remains more or less static. And now if we just vary the CP of the optical pulses by 0.2 pi, you see that there is a dramatic change of the waveform of the EV pulses, and this almost does not change for the case of EV emission from quartz. And so this, so with this experiment, it is we were able to demonstrate ultimate waveform reproducibility of EV pulses by doing high harmonics in quartz compared to gaseous targets. Now, in this experiment, one also has to be careful with the effect of the sample thickness on the phase of UV emission. So if you generate UV emission from thicker crystals, there can be some propagation effects or the Kerr effect, which can play some contribution, and this can also lead to some artificial effects. So in this kind of experiment, one has to be very careful about the artificial effects that can come into picture. So I would like to conclude my talk. So I have shown you that the UV emission in quartz, both for crystalline and non-crystalline, is actually dominated by intraband dynamics. This is the non-recollisional dynamics. And that the UV emission generated in solids is perfectly synchronized with the peak of the optical pulse. And we have shown that we can generate phase-coherent multi-PHz currents in bulk solids, and we can estimate quantities which are related to the dynamic conductivity of electrons in the bulk solid. And we have shown that the phase of UV emission in quartz is independent of intensity and CP of the optical driver. And in the last part of the talk, I have also shown you that by doing EUV generation in bulk solids, we can have ultimate waveform reproducibility of EUV pulses. And all this work was done in the group of Professor Eleftherios Kolimakis when he was still at MPQ in Garching, and now he has moved to Rostock. And these are the people who actually played the important role in this work over here. With this, I would like to thank you for your attention.
Thank you very much, Manish. Please, Fernando, yeah, go ahead with the question.
Yes, thank you, Manish, for this nice talk. I have one question. At some moment, you showed figures in which you represented energy as a function of the delay time or vice versa.
Yes.
Energy as a function of time, don't you have any problems with the uncertainty principle? I mean, can energies be defined as or not?
Actually,
I mean, no, I mean, often when you, how would I say, when you, if you want to have energy well defined, you need long time intervals. So
here, of course, I think the uncertainty principle cannot play a role because we are looking into only a relative time.
okay.
We are not looking into absolute time. So we are looking into the relative time of emission of the high energy photons with respect to the low energy photons. So we are not talking about absolute times here.
Okay, but even those times, yeah, but in order to talk about delay time, delay time is T1 minus T2. For it to be well defined, well, I don't know. Time is always relative in the sense that you are comparing two instants, right? So, I mean, I might understand that the time scales and time and energy scales are such that you don't have a problem, but in principle, it sounds a bit, well, maybe it's okay, but I just wanted to raise the point.
Yeah, but all this uncertainty will also cancel in this case. So the
Okay.
uncertainty in T2 is the same as the uncertainty in T1.
Okay. Okay.
Thank you.
Thank you.
Yes, more question? There is another one.
Yes.
Peter, please.
Yeah, thanks. Hello, yeah, Manish, thanks. Very nice talk. I have a question on exactly the same slide.
Okay.
So in the interband contribution, you're showing that the emission has a positive chirp, which
Yes.
is to, well, you said it's similar to the gas phase case, but in fact, it's very similar to the short trajectories in the gas phase case.
Yes.
Do you see in your simulation that there is a contribution of long trajectories?
Yes. So actually, if you solve the semiconductor block equation, of course, there's a contribution of the long trajectories as well, which will come over here. So you will have positive trajectory, positive chirp from the short and the negative from the long, similar to the gas harmonics. The only difference is actually in these simulations, you introduce a dephasing time, and this is a phenomenological time, and this is related to the scattering of electrons with respect to each other and also the Coulombic interaction. And this dephasing actually kills the other part of this polarization. So you see only this part over here.
Do you think that's realistic to have such dephasing time that exactly cancels the long trajectories but makes trajectories survive? Or is there a chance to also see long trajectories in some experiments?
So the thing is, of course, the dephasing time in solids cannot be measured very precisely. And the thing is, only we try to put the dephasing time in which we would get a reasonable spectrum in our experiment. And this dephasing time always turns out to be extremely short. And so in principle, from this kind of experiment that we did in SiO2, where the contribution is only intraband, there is of course not a possibility of this kind. I'm not so sure whether it can be done in, for example, in zinc oxide or another system. But the other thing is, of course, we cannot independently verify in attosecond streaking, because in attosecond streaking, the way the pulses are generated, most of the time they will have a positive chirp because of this macroscopic phase matching condition. And most of the times, even in the standard gas phase EV pulses, we don't see the negative chirp. We see only this part of the pulse. Okay. And this is, of course, not the case when you are trying to generate high harmonics from a much longer pulse. Then you, of course, you can see both positive and negative chirp as in one of the works from Qualcomm's group.
Okay, more questions? Thank you very much.
Well, I have another question. If there are, can I? It has been suggested, of course, that with these measurements of harmonics in solids, one might ideally map all of a sudden, just by fitting all the parameters, one might reproduce the band structure in a single experiment, ideally in a non-invasive way. Okay, so how far are we from that sort of dream, or we are already there?
So actually, since actually band structure reconstruction is a much complicated process. So in the recent work from the group of Professor Golim-Marquez, so what they have done is actually they have tried to reconstruct the valence potential of electrons in the real space. So because this is only one curve and it will not have so many bands and so on.
So they reproduce one band, but what about reproducing two band and conduction, say valence and conduction band, for instance?
No, so they have done everything in the real space. So in principle, there is also a work from the group of Rupert Hooper, and I think they have reproduced more bands, more than one, but I have not seen this. So this is in review, I guess.
No, but wait a minute. The band structure by definition is in K-space. So in real space is crystallography, which is fine too. But
yes, so they have looked into crystallography and they have ignored the reciprocal space picture.
Okay, so they get both. They learn about the real space lattice and the reciprocal lattice at the same time, in principle.
So in this work, I am not involved.
Okay, no.
But in principle, in the new work, they just talk about the real space, not the reciprocal space.
Okay, well, my question was general. Thank you for you.
Thank you. Yeah, I have a question myself. So in terms of efficiency of attosecond or intense attosecond pulse generation, so what do you think is the best scenario? I mean, the you can control, in principle, as far as I see, the intra and the interband process. So if you would like to generate an intense attosecond pulse, so what would be the best scenario for it?
So actually, the thing is, the solids, they have a much lower Dimas threshold. So you cannot expose them to very high intensity. So this is one limiting factor. But actually, if you just compare into the intensity range in which we do our experiment in solids, and also the intensity range where the experiments are done in case of gases, we have found that actually the solid is much more superior compared to gas. But of course, there is another possibility that people in principle can do the phase matching of EV emission. So they can stack several solids and look into the UV emission. They can add up UV emission. So this is of course another possibility. But so far, if you look into the high intensity gas-based sources, this is not compatible.
Okay, thank you. Yeah, Trung, please go ahead with your comment. Yeah.
Okay. Yes. Good morning, Manish. Very nice talk. Yeah, I just want to add a little bit on the very nice question from Fernando. So we did try to reproduce or to reconstruct partially the band structure with Manish, in 2015 papers. But additionally, there has been another work from Zetikov, maybe you know Lanin. So in Optica, volume 4, that also follow very similar track, and they try to reconstruct zinc selenized band structures from doing spectroscopy measurements, and they did reproduce to the very high accuracy compared to the density functional calculations. So just to add you additional information. Thank you. Very nice questions.
Thank you. Thank you very much. So more common question, please. So if not, please let's thank Manish, and we move to the second talk of this morning. Please, Thomas, could you share your screen and I will present you. Yeah. Okay, thank you. So the next talk is from Thomas Fennell, and the title is Origin of a Strong Field-Induced Low-Order Harmonics Generation in Amorphous Quartz. Please, Thomas.
Yeah, so good morning, everybody. So it's a great pleasure to contribute here to this mini colloquium. So I'm from Rostock mostly, so there my group is located currently, but I'm still affiliated with MBI, and I'm today talking about the origin of strong field induced low order harmonics from amorphous quartz. So that's obviously, as you can see here, the cooperation between MBI and Rostock. And so the goal of my talk is to convince you that there are indications for light from inside the tunnel. So just to quickly motivate, so some of these pictures have been shown, or these graphs. So the Gimmeyer work from zinc oxide nicely showed the odd harmonic progression and the cutoffs already scaling linearly with field intensity. And in particular, they also showed the nice non-perturbative scaling of the harmonics. And already in this paper, they suggested that the anharmonic structure of the bands is a major factor for the emission of these harmonics. And on the other side, the work by Corkum investigated also zinc oxide crystals with the mid-infrared laser plus its second harmonic in order to investigate the origin of the harmonics, and from the relative phase dependence, here written in terms of the delay, of the modulations of individual harmonic orders, they extracted these delays which supported the recollision, such that the model which we know from atoms is somewhat reminiscent also in the bulk, where we have the acceleration in the conduction band and the stimulated recombination, just similar to what we know from the atomic case. So, and as we have seen in the talk before, now for a real wide bandgap material with optical drivers, the Coulimakis team could observe photons up to 30 eV, which is quite remarkable, and they also attributed their emission, as we have just heard, to the anharmonic structure of the bands. So in a sense, to summarize a little bit the picture, we have strong evidence that there are important contributions from the intraband mechanism, which mostly is driven by the anharmonic motion of electrons being driven by the field through the conduction band and the valence band, that the holes are driven. And there are contributions from the recombination, as we all know from the atomic business, but there's probably also an important additional contribution, and that's the focus of my talk, and this is ionization. And ionization, which would correspond to the first step in the three-step model, may provide harmonics at least via two possible mechanisms. So first, there could be the interband excitation itself that could create a nonlinear polarization that creates harmonics, and there could be the field-driven intraband dynamics of just the time-dependent population of electrons in the conduction bands. So with this, I mean just the motion even in a harmonic conduction band that just takes place with a time-dependent population. So, and after this motivation, I come to my key questions. So the question is, are ionization-driven harmonics significant? And what could be the signatures and mechanisms? So in order to define the scenery a little bit, let me start with a seminal paper by Francois Brunel back from 1990, who looked at ionization-driven harmonics in the gas phase. And the idea there was to consider classical free electrons created from strong field ionization, so for example by tunneling. And these electrons then generate a current density, which of course just scales by the charge of the electrons, the density, and their average fluid velocity. And for radiation, we need the acceleration. So let's take the time derivative, which creates two terms as a product rule. The first term is just the derivative of the population times a velocity, but this velocity is basically the burst velocity of electrons that are created at the end of the tunnel in a tunneling picture. And there are reasons to argue that this is almost zero. So Brunel also neglected this term. And then there's also only the second term, which comes from the acceleration of the electrons that are already there. And we can just replace acceleration here by Q over m times electric field to arrive at this term here. So this is then basically the product of the population and the driver field. And so the population, if this unfolds due to, for example, tunneling rate, will create these steps. And these steps occur at each half cycle. So therefore, in the Fourier decomposition, you expect even multiples of the laser frequency here in this term, and just another omega in the electric field, which then leads to the expectation of odd harmonics. This picture is just taken from the old Brunel paper. So the question is now, is this relevant for at all, or even relevant for solids? So there's one important paper, one important work from Vienna, where they have looked at such a signature. So in this PRL here, they considered a setup like the following. So a short, intense few cycle NIR pulse and a longer femtosecond NIR pulse, slightly detuned, are overlapped in SIR2, and they looked at the mixing signal from these two fields. And the setup was prepared such that the probe field is orthogonally polarized, and the detector was organized such that the probe field must appear here in the field of our acceleration term, such that the pump field just creates a population and the probe field provides the oscillation. And this then leads to these sidebands here simulated and experimentally measured. And so the authors argue that this is ionization-driven signal because the lowest Fourier coefficient would have two pump photons in it, and the probe photon just comes from the acceleration here. So the problem is a little bit that it's not a smoking gun. So the argument for ionization-driven sideband signal here was the following. So the sideband signal almost vanishes if they switch to circular polarization. The logic is at first glance nice. So the idea is, for a circular polarization, you just have a smooth increase of the population and no more steps, and therefore the signal should vanish. But this argument does not hold. If you look closer into it, the signal would be even more intense for comparable field strengths, but I can discuss that later in the questions if you are interested. So here, just from this early experiment, there remains a question if this is really from ionization. So how much just comes from regular Kerr nonlinearity, and if it is ionization, what is the mechanism? Is it Brunel? So this is the starting point for our joint project between Rostock and MBI. And so here's the experimental setup, which is similar to the Baltuska work, but has an important difference regarding the pump field. We use a long wavelength pump field, the mid-IR pulse here that is strong to create, or to basically perform the ionization, and a weaker NIR probe field to control the wave mixing. So and here you see the spectra, it's the delay axis, and we see several orders. So the orders are indicated, the terminology is indicated here. So n equal 1 means just 2 pump photons, n equal 2 means 4 pump photons, and so on and so forth. So we observe even higher orders, and the most intense is a 3-photon signal. And so we think that we can rule out stimulated recombination here, because this is clearly emission below the band gap. However, there's still the question if the signal just stems from band anharmonicity or a Kerr-like response. And in order to check this, just the measurements were repeated with crystalline SiO2 sample. And so upon rotation of the sample, it is clear that this n equal 1 harmonic signal, which is a 3-photon signal, has a crystal orientation dependence for low fields, which we would expect for Kerr, but this rotation dependence vanishes for high intensity. So, and we conclude that it's unlikely that the signal stems from intraband anharmonicity, because otherwise we would expect clear rotation dependence in the signal. So there, the question remains if we can rationalize the observations by the ionization-driven nonlinearity. So, and therefore I'd like to present our modeling, so which is a local plasma model. In a sense, it's extended based on the idea from the Brunel paper. So the acceleration term is shown here with additional terms. So we have the Brunel terms that you know already. There's the burst velocity term that just considers to the initial velocity at the tunnel exit, which we also neglect. And there's an important additional term, the injection current. And the injection current, in a sense, describes the motion of an electron through the tunnel. So the appearance of an electron at the end of the tunnel or in the conduction band is associated with a spatial displacement, or it must be associated with a spatial displacement to maintain energy conservation, because the field energy has to be removed from the field to fulfill energy conservation. And there's also the Kerr term. And so the last point is now, if we simulate this with pulp and probe fields as in the experiment, we can compare signals for parallel and perpendicular polarization of these two fields. And that's very nice, because if you consider the process to be described by such an effective nonlinearity, then the parallel configuration is expected to produce much more intense signal. And in detail, if you associate an effective order here, 2 mu plus 1, to this nonlinearity, you would expect to directly see the effective order of nonlinearity by just comparing the signal ratios. And with this, I can come now to the main slide of my talk. So here's the main analysis of the observed signal here in purple for n equal 1. So here you see the intensity ratios for parallel and perpendicular field configuration and the associated effect of nonlinearity. And starting from a value of about 3, it slightly increases and then makes a big jump to nonlinearity orders beyond 10, close to the damage threshold, which is indicated here by the color. And the important point is now that this nonlinearity, effective nonlinearity, can, of course, by no means be explained by the Kerr contribution, which just leads to an M of 3, and it also cannot be explained by the Brunel term. Only if we include the injection term, we get a very nice agreement with the experimental observation, and this also holds for the higher order n equal 2. So you could now ask, maybe this is just a feature that is very sensitive to the details of the ionization rate, but in fact you can play a lot with the ionization rate, for example, change the band gap or effective IP quite a bit, and only the step position shifts, but the dominance of the injection contribution does not change. And that's even more clear if we now look into the relative contributions of the injection term, the Brunel term, normalized to the Kerr contribution. And for a wide intensity range, the injection is much more intense than the Brunel contribution and outperforms beyond a certain threshold also the Kerr contribution here for amorphous quartz. So that's essentially here the main conclusion. So we think that we have found strong evidence for the presence of ionization-driven harmonics near the damage threshold in both crystalline and amorphous quartz. And it's very interesting that the signal seems to stem really from the injection current. So in a sense, that's a current through the potential barrier in a tunneling picture, but it's not restricted to the tunneling picture, of course. And this is dominant over the previously considered Brunel and the Kerr term. And this could allow really a tracking of sub-cycle dynamics of strong field ionization with the corresponding two-color approach, which may use also few cycle MIR fields, or maybe such nice fields as the Guillemarcus crew is using. And so we expect wide applications here for this low order wave mixing, and also of the idea of this effective nonlinearity for characterizing processes. So we have seen that just identifying the processes is not always easy. And so with this, I hope you now see what we mean if we say that this harmonic emission seems to be light from inside the tunnel. And at the end, I would like to acknowledge the work. So from my group, the key people are Björn Kruse, Benjamin Liewer, and Christian Pelz. And from the Max Born Institute, Peter Jürgens was a PhD student that performed most of the experiments under supervision of Alexandre Mamilot-Blondon, and everything was done together with the groups of Misha Ivanov and Mark Racking. And with this, I'm done and like to thank you for your attention, and I'm happy to take questions.
Thank you, Thomas. Thank you for being on time. Thank you very much. Thank you. Please, question and comments? So I have a question regarding the material. So what is special about quartz, or do you think this can be studied in many other materials?
Yeah, so I think it can be studied in many materials. So in a sense, the motivation was to use one of the most important materials for practical applications. And so amorphous quartz is everywhere. And if we are able to maybe track the subcycle dynamics of ionization, this could really be helpful for monitoring and maybe even optimizing machining processes. So, and I think that would be another very powerful application of harmonic emission or nonlinear wave mixing in solids that could really be important also for production relevant processes. And in a sense, this was a story that developed by coincidence. Initially, we were thinking that we are just observing the Brunel signal, and we wanted to make just a tomography or just a reconstruction of the dynamics. But then we found out that it's not possible to rationalize the emission, and that's one of the nice things about science, that's sometimes under your nose, and then you find an interesting new aspect. And of course, it's important to repeat such analysis for other materials, and also to continue comparisons with maybe more advanced simulations. But at the moment, we think that the signature is a quite strong smoking gun for the presence of ionization-driven nonlinearity.
Okay, thank you. Yes, Peter, go ahead with the question. Yeah.
Thanks a lot for this interesting talk. And I apologize for the weird noises that my laptop is making and you will be hearing now. This one. So we've already heard in previous talks that the infraband contribution might be very important for quartz and fused silica at high energies. Now you basically discovered that injection current contribution, and as I understand, mainly at lower energies or lower harmonics. Do you think it will also be important at higher energies, or do you think there will be a switch at a certain energy?
Yeah, so I think it's definitely a point that deserves more attention. We have seen by the work from many theory groups that initially also the interband mechanism was assumed to be much more efficient, and then the picture started to change a little bit. So I think we should not exclude also the relevance of this mechanism for even higher orders, but of course it's then probably even more difficult to identify the mechanism. But I think worthwhile to keep this on the table, and even in the 2015 paper by Wampa from the Corpus group, they already considered this contribution, or the Brunel drift contribution, as one possible route, and just did put it to the side because of the relative phase dependence. But for example, for other materials or at parameters close to the damage threshold, also this could really change. Yeah, so I think the story is not over, because typically people try to stay away from the damage threshold to keep using their targets. for a longer time, but maybe it's just for other applications, it's an important sweet spot to be at the damage threshold or even beyond. Yeah, so that's also interesting to look at a situation where you really destroy the material, maybe with a moving target, where you have a fresh sample each shot and even go into the damaged region. So this is something we definitely want to do.
Okay, thanks.
Last question, Dieter, please. Go ahead. Yeah.
Yeah, thank you, Thomas, for this very nice talk. It would be great to make some connection to a microscopic quantum description somehow. So do you think that in a two-band model system where you really solve the equation of motions exactly, like it was presented yesterday by Daniel Moos, your term should be there or not? I think it should be there, and we just have to pull it out somehow.
Yes, exactly. So I'm absolutely sure that it will be there, and maybe I was not clear enough in making this point. I just would say that the ionization-driven contribution is not just an intraband or an interband process. It belongs to both. So this terminology doesn't make sense to discriminate this process from others. And I'm absolutely sure that it's already contained in the Wampa calculations made together with Thomas Brabeck, but it's not possible to just identify the process by looking at the signal from intra and interband currents. So our idea or our hope was here that this step feature, which is associated with a strong increase of population due to ionization, is a better smoking gun to identify the process. I'm absolutely sure it must be there. The question is just how to extract it and how to isolate the contribution. Probably one can try to make a spatial analysis of the current where polarization terms and terms that result from tunneling are maybe identified by a spatial mask or whatsoever, and by that might be hoped to also extract that from a two or multi-band description, but it must be there, sure.
Thank you.
Okay, thank you very much, everyone. Thank you, Thomas, for your talk. And please, we can move on to the next talk now. The next talk is Attosecond transient absorption spectroscopy in condensed matter system by Giovanni Cistaro. Please, Giovanni, share your presentation and start. Thank you very much.
So good morning to everybody. I'm Giovanni Cistaro. I'm a PhD student at the Universidad Autónoma de Madrid at the chemistry department, and I'm very glad to be part of this conference. So this work has been in collaboration with the University of Salamanca, in particular with Luis Plaja, and the name of this talk is Attosecond transient absorption in condensed matter system. So first of all, I would like to outline more or less what I'm going to talk about. So
sorry, would you please put it in presentation mode, or because?
Okay, yes.
Sorry.
Okay. Now it's fine, no?
This is perfect. Thank you.
Okay, thank you. So I'm gonna give a brief introduction to Attosecond transient absorption spectroscopy for those of you who are not familiar with this. Then I am going to talk about the model that we use to model the equations of motions in solids with the two lasers. And then I'm going to show the Attosecond transient absorption spectrum in a benchmark material that we use, that is graphene. At the end, I will give the conclusion and the output. So let's start with the short introduction to ATAS. So the first question may be why we want to use attosecond passes. So 1 attosecond is the shortest time that we can reach with a laser pass. We can reach it only, we managed to reach it only in the last decades, thanks to the novel technology that uses high harmonic generation. So the importance of attosecond passes is that attosecond is the natural time scale of electrons. So here I put a simple picture of the semi-classical model, Bohr model of a hydrogen atom. So we say that the Bohr radius is half angstrom, and the velocity of the electron inside the 1s orbital is 100 of the velocity of the speed of light, so 2 kilometers per second. We can calculate that the time for the electron to travel a Bohr radius at this velocity is 24 attoseconds. So it really moves in this time. So what is transient absorption spectroscopy? So there are two different pulses. A first pulse, there is a pump, there is very broad in time, and the second pulse, there is the probe, there is very short in time that we use to follow the dynamic of the excited states. So the idea is that we measure the dynamic of the electrons when we so the absorption spectrum when we change the time delay between the pump and the probe. So the probe will excite from a core level to an excited state, and then with the pump we will make interference between this state and other states. So what is an attospectrum? So first of all, we measure two different absorption spectra. Well, one when only an XUV pulse is acting on the system, and the other one when this excited state is perturbed with an IR pulse. And so by taking the difference of these two absorption spectra, we obtain what is called transient absorption spectrum. And by taking several transient absorption spectrum, changing the time delay, we get the transients, we get the final spectrum in 2 dimensions. And so we expect that at different delays, we will really capture the electron dynamics. So why we want to do attosecond spectroscopy in solids? Because one might think that we add other bands that are the core bands, so we add more information that is not needed. But in fact, the core bands are flat in K space, so there is not a lot of information coming from this. And moreover, the core hole decays. So once the XUV excites in the conduction band an electron, it decays in a few femtoseconds. So we can really get information that is instantaneous. And moreover, we noticed that by making our calculation, the intraband dynamics induced by the IR is sensitive to important information about the system, such as the band dispersion. And finally, the main feature of the attosecond transient absorption spectrum in condensed matter appear to be only at one-off singularities. They are the most important points in the K space. So let's see how we are modeling this the equation of motion. So here we have the equation of motion in condensed matter. So we are using the von Neumann equation of motion in K space. So we have the density matrix formalism, and in particular, we use the reduced density matrix in K, and we work in the length gauge. So what we say is that our Hamiltonian is the Hamiltonian of the system, of the condensed matter system, plus a term that is time dependent, and in particular is equal to the usual electric potential. So what is particular in condensed matter is that the position operator takes this weird form. So we have a contribution that is from the Berry connection, and another contribution that makes the system goes forward in the K space, and this term. Last, we add another term that is the first one is in this equation. So we say that the derivative with respect to time of the density matrix is proportional to the density matrix itself. And this is because we need an empirical dissipation term, since we are not considering a lot of dissipating effect in our system. So here is how we make the calculation. So this is the scheme. So we have 3 different regions in the energy space. We have a core region that we are considering. Then we have a lot of bands that we don't consider because we expect that are not contributing in our dynamics. And this is what people in quantum chemistry, in particular in the method CAS-SCF, is doing right now. And then we have the valence and conduction band. So in our calculation, since the bands are flat in K-space, we can already work in the diagonalized basis for core levels. While for valence and conduction, what we have to do is a transformation in the wave function space. So what we do is to rotate the eigenvectors in such a way that everything looks smooth in K. And last, for the x-axis, note that here we don't have K, but we have K plus a term that depends on time. And this is what is called canonical quasi-momentum. So we work in the accelerated frame. So we are really following the electron dynamic inside the band. So we use two pulses. The XUV couples the core band with the conduction and valence band, but doesn't couple the bands inside the same region. The other pulse, that is the IR, can only couple bands inside the same region, and moreover, it moves the K-space. So to go to the observable, we need to calculate the dipole in time. So the dipole in time is given by this formula. And what we do is to work in the rotating wave approximation. So we don't follow the dynamics of the XUV, but we smooth everything. So we follow only the envelope given by the IR. And in this approximation, what happens is that the main contribution of the dipole in time is given only by the coherence between core hole, that here I indicate with C, and valence and conduction band that I indicate with B. So the dipole in time will depend on the density of the coherence between these two bands and the Berry connection. And at the end, to obtain the observable, we calculate the absorption response of the system as the imaginary part of the Fourier transform of the dipole multiplied by the conjugate of the electric field. So now I want to show you some preliminary results that we obtained for graphene that we use as a benchmark material. So first of all, I want to point out how we model graphene. So we work in a tight binding basis. So our wave function in K is a linear combination with the usual phase factor of atomic orbitals displaced in the R space. So the minimal basis for this calculation is that we have two orbitals, two core orbitals, one for the sublattice A and the other one for the sublattice B, and two valence and conduction orbitals. So these are the orbitals that are really forming the chemical bonding, and there are two p orbital of carbon in the two sublattices. So the Hamiltonian, as I said, it will be already diagonal for the core bands, and we'll have the energy of the K edge of carbon, so 296 electron volt, while the Hamiltonian for the valence and conduction block will be non-diagonal. And here are our results that we obtained. So we use a frequency of the IR of 0.41 electron volt that corresponds to a wavelength of 3 microns, and an XUV pulse that is exactly at carbon K edge. And at the best of my knowledge, this is the first spectrum that somebody got from the carbon K edge. So we work with an XUV of 296 electron volt. And what we can observe from the spectra, so here on the top, I have the gray line, that is when we don't have the IR, and the red line when I have both XUV and IR, and here I plot the difference. And the main differences are corresponding to the Ivanov singularities. In particular, we have differences at K, M, and gamma. So what happens is that the IR is already strong enough to inject electron from the conduction to valence. And this explains the part of the spectra that is close to the Fermi energy, so this part, because when the electrons are pumped with the IR from the valence to the conduction, when the XUV comes, we can inject less electron from the core bands, so we see a decrease of the absorption spectrum. And the same can be said for the valence band. This is just a matter of the Pauli exclusion principle. So what happens is different at M and gamma, because only with the IR we cannot inject electrons from the valence directly to the conduction band. So these 2 points are really, there are drastic changes that are really coming from the effects of the electrons coming from the core levels. So what happens is that the electrons is promoted from the core band to the conduction and valence band, and then thanks to the IR, this moves in the K space and produce this spectra. And this spectra is not null, only corresponding to Van 't Hoff singularities. Last, I want to point out that the spectra has different symmetries at gamma and M. And these symmetries, we think that come from the band dispersion. So at gamma, we have a shape that is similar to what we observe in atomic system. And this is because the gamma point is a parabola in K, while at M, well, we have another shape. We see an antisymmetric spectrum that is quite new. Finally, this spectra that I'm plotting here is corresponding to a time delay of 0 femtosecond between the IR and XUV. If we do the same after 5 femtoseconds, we see that the difference between the red line and the gray line is almost 0. And this tells us that from the ATA spectrum, we can really retrieve the time decay of the core hole, because 5 femtoseconds is the lifetime of the core hole for us. Okay, so I want to give you some conclusions. So the method that we developed seems to be valid for future investigation of real experiments, and so to exploit material both in 3D and 2D. So the ATA shows important feature, and in particular, we expect that we can retrieve the energy dispersion corresponding to Van 't Hoff singularity by the symmetry of the spectra. And then we can say something about the dynamic where we have injection of electrons, in particular here at the Dirac cone. And our outlook is that we want to try to use circular polarization to see what happens, since we know that everything about topological insulator, that is what we are going to study, we want to study, is important with circular polarization. So when we close a loop in K space. Okay, so that's it. Thank you for your attention. And
thank you very much, Giovanni, for the very nice talk. So we have 5 minutes or 3-4 minutes for question, please. So I have a question related with the dimensionality. So your model is 3D from scratch, or can you use any kind of complex field to drive the dynamics, or this what you show is only for linear polarized? Right?
So this spectra is for linear polarization, but what we want to do now is to use circular.
Okay, so you can put 3D configurations. Okay.
Yes.
Some more common questions? Okay, so we can move to the next talk. Thank you, Giovanni, for your time. The next talk is from Davide Facciala.
Yes, can you hear me?
Yes, our high order harmonic generation spectroscopy of zinc telluride. So I was looking for the name. Thank you. Thank you very much. Please go ahead.
Okay. So you see the screen, right? Okay, good morning, everyone. First of all, I'd like to thank the organizers for giving me the opportunity to present at this conference. I work in the ultra-fast dynamics in matter group in Milano, and today I present the recent results we achieved on high-order harmonic generation in zinc telluride. So let me first quickly go through the outline of this talk. I start with a brief introduction of HEG as a spectroscopy tool for probing matter. Then I describe the mid-IR intense few cycle source that we developed to generate high harmonics in solids. We use this source to generate harmonics in zinc telluride crystal, and I'll show you the main results that we obtained. Finally, I'll end with some conclusion and future perspectives. So, well, you all know why it's interesting to use HEG as a spectroscopy tool. By exciting matter with a strong laser field, we can study electronic processes in their natural scales, the attosecond time scale and the sub-nanometer scale. The HEG process triggered by the laser in a gas target can be easily understood within the semi-classical three-step model that you all know. An electron is first detached from the valence state of the system. It is then accelerated in the continuum by the laser field, and after a certain time, it can recombine with the ion emitting a high energy photon. This description in terms of trajectories allows to give a straightforward interpretation of HEG as a self-probing spectroscopy tool, where basically we take an electron from the system and use it to probe the system itself. And this is possible due to the fact that the ionization and propagation step are less sensitive to the target. So we can use the scattering of the electron with the system during the recombination step as a high sensitive probe of the orbital structure, which is then encoded in the emitted radiation. And this allowed, for example, to perform a tomographic reconstruction of the HOMO orbital of CO2 by looking at the HEG emission from molecules aligned each time at a different angle with respect to the laser polarization. So HEG thus offers a unique tool for probing the structure of a system with high resolution. So coming from this background, we wanted to move to this new field of HEG in solids. And in a solid, the picture is a little bit more complex, but offers at the same time new interesting perspectives. So in this case, we can still use a three-step model to describe the process, where in the first step, we have a creation of the electron-hole couple. In the second step, the propagation of electron and holes in the respective bands. And in the last step, the electron-hole recombination. The remarkable difference with respect to HEG in a gas is that now we have emission of radiation, both in the propagation and in the recombination step. And also, as you learned today from the talk of Thomas Fennell, probably also in the ionization step. So this means that we have a higher sensitivity to the structure of the system with respect to HEG in gas. And this allowed, for example, the reconstruction of the band in an all-optical fashion, non-destructive way, as performed by Vampa and other authors. And also it means that polarization, it's interesting to look at the polarization and the helicity of the HEG emission, as also we learned yesterday from the talk by Silva in the yesterday morning session. So there's, however, one fundamental experimental drawback of HEG in a solid with respect to gases, which is the low damage threshold of a solid when it is exposed to an external laser field that limits the use of arbitrary high intensities. So typically longer wavelength and few cycle pulses are needed compared to HEG in a gas. So we went back to the lab to laser development, and we developed a high energy few cycle laser source working in the mid-infrared energy region. This is a scheme of the setup we developed for generating this mid-IR source. Our front-end laser is a commercial titanium sapphire laser working at 1 kHz repetition rate. We first generated a white light inside a hollow core fiber filled with krypton. This wild light is then compressed, and it's focused inside a potassium titanium arsenate crystal, KTA, for generating the mid-IR seed, which is generated by intrapulse difference frequency generation from the white light. Then the seed is amplified by two optical parametric amplifiers in cascade, exploiting again two KTA crystals as an amplification medium. Finally, the pulses are compressed by using silicon and calcium fluoride plates. And for the details of this setup, I would like to direct you to the paper of Mikhail Mushegian, who worked with our group for the development of this source. Here you can see some feature of our source. The OPA is tunable from 2.4 to 4 microns, which gives us some degree of freedom in choosing the wavelength for generating harmonics. It provides pulses of 360 microjoules at 3.4 micron before compression, while after compression we have 300 microjoules. And anyway, energies higher than 80 microjoules are observed in all the entire turning range of our OPA. After compression, the measured pulse duration was 52.5 femtosecond, which is really close to the transfer limited pulse duration and correspond to 5 optical cycles. The source is also passively CEP stable, and we measure the root mean square of our CEP of about 300 milliradians over a 20 minutes of observation time. So this can potentially allow to study the role of CEP on the HEG emission. So once we had this source, we wanted to test it for generating harmonics, and we tested on a zinc telluride crystal. We chose this crystal due to the fact that it is not centrosymmetric, so we expect to generate both odd and even harmonics, and due to the fact that it has a band gap of 2.26 eV that is suitable for our 3 micron source. The first setup we implemented is very simple. The laser first passes through a linear polarizer here to remove any possible residual field in the orthogonal direction. Then a broadband halfway plate is mounted on a motorized rotational stage, and it is used to control the direction of polarization of the laser field. And in the end, the mid-IR beam is focused in a crystal, and the emitted radiation is collected and focused again inside the spectrometer, where we use alternatively a visible or a near-infrared spectrometer to cover all the region of harmonics emitted by the sample. We then, our ZNT sample was cut along the 110 plane, where atoms lying on this plane, which are represented here as big dots, they form a zigzag chain. And when we look at the neighbor planes on top and on the bottom of the one highlighted in yellow, the smaller dots lying on this plane also form a zigzag chain, so that when we look at the whole projection of the crystal in this plane, there's this honeycomb structure that can be seen. Our polarization is tuned, as we said, with an half-wave plate. It can be tuned with an half-wave plate, and it always lies on this 110 plane, since the propagation of the laser is perpendicular to the 110 plane. We then measure the HEG emission along 2 characteristic directions of the crystal. The spectrum in blue shows the harmonics emitted when the laser is polarized along the direction that connects 2 first neighbors of different kind, while the spectrum in red instead shows the harmonics emitted when the laser is polarized along the direction that connects 2 first neighbor atoms of the same kind. So it can be seen first that harmonics up to the 8th order are generated, which is beyond the band gap energy of ZNT. And then that both an odd and even harmonics are produced. And finally, it can be seen that the intensity of even harmonics is reduced when the laser is polarized along the red horizontal direction. We then studied the HEG emission for different directions of the laser field, making a complete scan of the HAG signal as a function of the polarization angle. It is possible to observe strong modulations, and they look different for even and odd harmonics. So to analyze more carefully these results, we can make polar plots. We can make polar plot of the normalized intensities of harmonics as a function of the polarization angle. On the left, you can find the even harmonics, and on the right, the results for all the harmonics. We can observe a clear four-leaf clover pattern in all the even harmonics, with lobes which are directed along the plus 60 and minus 60 degrees directions. For all the harmonics, instead, additional lobes appear at 0 and 90 degrees. So coming from a background of HAG in gaseous targets, we try to give a very simple description, very naive description of these results in the recollision three-step framework. So in this simple model, we assumed that first, electrons are ionized from one side of the crystal that can be either zinc or tellurium, and that after ionization, they follow a trajectory which lies on the laser field polarization direction, here represented as a blue arrow. Then we assume that the probability P of the electron to recombine with one of the neighbor ions is proportional to a Gaussian, where D is the distance of the neighbor atom from the direction of the trajectory, and R is a free parameter of the model. Then we took into account that when the electron is ionized from an atom of one kind and recombines on an atom of a different kind, as shown here in the left plot, the radiation emitted is expected to contribute to both even and odd harmonics, since this process shows lack of inversion symmetry. There's no inversion symmetry in this process. On the contrary, when the electrons are ionized from one atom of a kind and recombine on an atom of the same kind due to the presence of an inversion symmetry in this process, the radiation emitted is in this case expected to contribute only to the odd harmonics. So we only consider the recombination with close neighbors, highlighted in the picture, and we can retrieve the expected emission for even and odd harmonics, which is here represented in light blue. As can be seen, we can retrieve the four-leaf structure of even harmonics that comes from ionization and recombination of two neighbor atoms of different kind lying on the same plane. For odd harmonics, we can see an additional lobe appearing at 90 degrees that comes from ionization and recombination of first neighbors atom of the same kind lying on the same plane. However, the lobe at 0 degrees here visible for the fifth and for the seventh harmonic in the experiment is not observed in the model. And this is probably due to recombination of further neighbors that are not considered, like the one highlighted here circled in green. So to conclude, we presented a tunable CEP stable mid-IR OPA source for HAG in solids. We demonstrated HAG in a semiconductor crystal up to the 8th harmonic order, and we characterized the emitted harmonics as a function of the polarization direction of the laser field. We showed then that this simple recollision model loaned from the three-step picture indicates that the HAG signal encodes the structure of the system probed. Obviously, we would like to go beyond this. One of our goals for which we are currently working is to study the polarization properties of the emitted harmonics. And this is essential if we want to decouple the different sources of symmetry breaking in the solid. We'd like to test this source on other sample, of course, and we plan to excite the sample with other pulses or tailored multicolor fields. And for this purpose, I'd like to highlight some of the capabilities offered by our Udini laboratory. we have a few cycle at 100 nanometer pulse. We have an additional intense few cycle OPA working at 1.5 micron range, and an XUV source of harmonics in gas cell reaching 300 eV. We also have in the lab a terahertz line, which is managed by Eugenio Cinquanta, here circled in green, who is basically the one for our group that comes from the condensed matter physics field. So he also works with us for this project of harmonic in solids. And I like also to thank, now that we have this nice picture of all of us, Aditya, Pusala, and Prabhash Prasannan, here in red and orange, that worked a lot in the lab for these experiments, in particular Aditya, that is also presented yesterday, the poster here, and my bosses, Caterina Bozzi and Salvatore Stagira. And finally, I'd like to thank you all for the attention, and I'm open for questions.
Thank you very much, Davide, for the very nice talk. We have time for questions now. So I have a question. When you say ionization, it's not truly ionization. I mean, you are talking about creation and holes and pairs. How do you treat this? I mean,
sorry.
But when you say ionization, it's not truly ionization. So you are talking about creation of holes and electrons, and how you treat this step. I mean, you don't ionize. So you promote electron from...
I sorry, ionization, yes, because
I understand,
promoting the electron on the conduction band, yes.
Okay, but you promote to where? I mean, how much energy, or how you tune this? So you say, I move this electron from here to there, and you tune this.
Yeah, obviously in the model we are not considering this. It's just we assume that the electron is free to move with the laser field. It's just, obviously this is a very naive model. It's not the case. Obviously you promote the electron in the conduction band, but let's say that we took this model from what we are used to do in the gas phase to see if it was possible to, let's say, have an interpretation of this, of what we observed in terms of trajectories. Obviously here we have many more complex things, and as for example, the first assumption that I'm making, that the electron travel the trajectory which is directed at the laser field polarization, is expected not to be true, since we have the Berry phase that changes the direction of the electron, that can also travel on the perpendicular direction with respect to the laser field. We have also the anisotropy of the crystal that just can change the polarization of your emitted harmonics. So it's just a very naive description that could in some way connect with, let's say, a tomography approach, where we see what happens in one direction and we try to see if it is connected to the structure. And in some way, yes, we have an understanding of what we see in terms of the structure. To decouple all other sources, yes, we need to probably make more experiments in two-color or multicolor fields, or elliptical fields, where we can see how the ellipticity changes and measure the polarization of the harmonics in the end.
Okay, thank you very much. More questions? Okay, so I don't see anyone asking questions. We can move to the next speaker and wait maybe 2-3 minutes. Yeah, someone has questions? Okay, so thank you very much, Davide. Yeah.
Thank you.
So the next speaker is Ana Garcia Cabrera. Please, can you share your screen? And
yes,
the talk is about signatures of electronic Talbot revivals in AJG from a one-dimensional crystal.
Okay.
Thank you very much for being here.
Good morning, everyone. My name is Ana Garcia Cabrera, and I am a PhD student in the Aplicaciones del Láser y Fotónica group at the University of Salamanca. First, I would like to thank the organizers for giving me the opportunity to present our work. I'm going to talk about the electronic Talbot signatures in the harmonic spectrum from a one-dimensional crystal, a work carried out together with Carlos Hernández García and Luis Plaja. High-order harmonic generation is a thoroughly studied mechanism in atomic and molecular gases. Its capacity to produce high-frequency coherent radiation emitted in the form of attosecond pulses makes it a robust technique to study ultrafast phenomena. In gases, we can understand easily this process through the so-called three-step model. First, due to the interaction of the atom with the laser pulse, electrons are liberated by tunnel ionization. Then the free electrons are accelerated by the electric field. When the field changes its sign, the electrons come back accelerated to their parent ions. During recollision, the generated oscillating dipole emits radiation in the form of harmonics of the laser frequency. HEG in atomic and molecular gases has provided great results. However, the required setup is still quite complex. This, together with the desire of getting higher efficiencies, has triggered an increasing interest to drive HEG in solids. This mechanism in solids is usually better understood in the reciprocal space. The emitted radiation in this case has two contributions: interband transitions and intraband transitions. This process has been observed in bulk solids, but also it has been studied in low-dimensional systems like graphene. It is interesting to mention that for low-dimensional systems, we can consider two different scenarios depending on the polarization direction. In the case above, the driving pulse polarization is contained in the plane, and the HEG process must be studied in terms of interband and intraband transitions. However, when the polarization is perpendicular to the surface, the HEG mechanism seems to be very similar to the atomic and molecular case. Later, we will interpret our results in the SFA framework. Strong field approximation considers that once the wave packet is ionized, its interaction with the atomic potential is negligible. It is widely used to study harmonic generation in atoms or molecules, but it is in principle not valid in solids due to the relative closeness of the atoms. However, as we will see later, SFA will be useful to us because we will study a similar situation to the second scenario. What we study here is the electronic Talbot effect in the ionized electronic wave packets during the process of high-order harmonic generation. This phenomenon is analogous to the well-known optical Talbot effect. Just to remind quickly the optical Talbot effect. This is a Fresnel's diffraction phenomenon first observed in the 19th century. When we have a periodic field distribution, like that in a diffractive grating, for example, we observe in the near field a series of self-images of the field distribution at regular distances from the diffraction mask. This kind of images, usually called Talbot carpets, represent the light intensity along the propagation distance and the transverse distance, in which the electric field is periodic. As we can see, there is a series of planes that are particularly interesting. At a certain distance, we find a perfect image where we recover the field distribution in the mask. We call this distance the Talbot distance. In the middle, we have an inverse image. Here, the maxima and minima are shifted with respect to the initial distribution. There are also sub-image planes which have higher periodicities, higher frequencies. Now, as the Schrödinger propagator for a free particle is mathematically analogous to the Fresnel propagator, we can translate this near-field diffraction experiment to matter waves. Just for illustration of matter Talbot effect, I'll mention two works with electrons. The first one is a theoretical work about electron diffraction in graphene. They study the Talbot effect for an electron beam with perpendicular incidence on a graphene layer. As we can see in the plots of the probability density, they found perfect and inverse images at the corresponding distances, following the honeycomb structure of graphene. The second one is an experimental work about an electron Talbot interferometer. Here, a collimated electron beam is diffracted by two nanofabricated gratings. After the first one, Talbot images appear. The second one is useful for retrieving the Talbot carpets in the detector by doing a scan in the transverse and longitudinal direction. Finally, they find different Talbot distances depending on the energy of the electrons. But can we play with the wave function evolution in a crystal with perpendicular laser polarization? In our case, we are interested in Talbot effect in the ionized electronic wave packets in an HEG experiment. If we introduce an electric field, the electrons are not traveling with a constant velocity, so we must change our framework. We are not using the distance from the initial distribution anymore, but the evolution time. In this situation, we can define the Talbot time as the necessary time to recover the initial shape of the density of probability. To observe Talbot effect in the ionized wave packets, we consider a linear crystal with a periodic wave function in one direction and a laser pulse with transverse polarization. The laser pulse liberates the electrons so they can evolve in the absence of the atomic potential. If we look at different instants of time, we find that the transverse distribution evolves forming inverse and perfect images. These plots correspond to a simulation for atoms separated by 20 atomic units. In the first frame, we observe the beginning of the ionization coinciding with the field maximum. In the following frame, the transverse evolution of the ionized wave function gives rise to an inverse image. The maximum of the density are shifted with respect to the initial state. In the third frame, the density is evolving towards a perfect image shown in the last frame. Although this case is not realistic, it allows us to observe clearly with a time scale similar to the laser cycle, the formation of Talbot images. Now we consider a more realistic case with a lattice parameter of about 2 angstroms. What we study here is a one-dimensional crystal in a two-dimensional space. To model this, we use a Matthew-type potential in the crystal direction and a Coulomb potential in the perpendicular direction. The parameters have been chosen for the system to resemble the carbon allotropes like carbine. This is the energy band scheme we obtained from the potential. And in this case, we are considering, for simplicity, a one-dimensional crystal, but it is reasonable to think that we can extrapolate this scheme to systems like graphene. To study the higher-order harmonic generation process, we choose different states in the lower band, and we solve the two-dimensional time-dependent Schrödinger equation using a combination of Kran-Nicholson and split operator methods. Then we compute the harmonic spectrum as the Fourier transform of the mean value of the acceleration operator. For a driving wavelength of 800 nanometers, we obtain the following spectra, depending on the initial states. Let's see what happens if we consider 1 state, 2, 4 states, and 10 states. Each state produces a series of plateaus at different frequencies. These frequencies follow a specific rule, as we will see later. Also, our spectrum extends well above the typical HEG cutoff. Note that the plateaus beyond the HEG cutoff seem to have the same structure as the single atom spectrum, with the negative and the positive part. The black curve represents the harmonic spectrum we expect for an infinite number of states in the band, and it is calculated from the interpolation of the purple line local maxima. As we have seen, the harmonic spectrum obtained depends strongly on the different states in the band. So it is interesting to see what happens if only half of the lower band is occupied. The purple line represents the spectrum for the complete band, and the yellow line corresponds to the spectrum for the half-filled band situation. Here we observe a series of holes corresponding to the states that are not occupied. So the spectrum gives us an idea of the Fermi level. But how can we understand these ultra-high frequencies that appear in the spectra? To understand these spectra, we resort to the strong field approximation. The initial states are block function, eigenstates of the crystal potential. We introduce the interaction with the electric field in the perpendicular direction, and we express the electronic wave function as a superposition of the field-free evolution of the eigenstate plus the ionized wave function. This ionized wave function can be expressed as a superposition of wave packets ionized at different instants of time. We are interested in the time evolution of the density of probability along the crystal direction. This density of probability can be understood as the image of the matter wave formed by a superposition of different sub-images. Each sub-image follows a dynamic of Talbot revivals with a Talbot frequency. As the Talbot frequency is different for each sub-image, there isn't a full revival of the complete ionized wave function. The harmonic emission is described by the real part of the dipole acceleration matrix element. The total dipole acceleration is the integral of the contributions of the electrons ionized at different instants of time. In our case, each contribution to acceleration has one part corresponding to the evolution in the crystal direction, where Talbot effect appears, and another one corresponding to the evolution in the polarization direction, which is similar to the contribution for a single atom. Every contribution is oscillating with frequencies that only depend on the periodicity of the wave function. We call this the Talbot frequencies. The different spatial frequencies contained in the electronic wave function give rise to different Talbot frequencies during propagation in free space. The signature of this process in the spectrum is the repetition of the atomic-like HEG spectrum at these Talbot frequencies. So the coherent process of Talbot revivals during the excursion of the ionized electrons in the HEG gives us information about the wave function structure through the harmonic spectrum. Just to conclude, through the numerical resolution of the TDSE in a linear crystal, we find electron Talbot effect in the ionized wave packets. As Talbot frequencies are linked to the wave function spatial structure, electron Talbot effect could be a useful spectroscopic tool. Also, this is a way to produce ultra-high frequencies, well beyond the HEG cutoff. So that's all from me. Thank you for your attention.
Thank you very much, Anna, for the very interesting talk. We have plenty of time for questions. Please, don't be shy. So I will start. You know that these different plateaus means that you are coupling with different bands. So this is the same here, or I mean, when you use
here, these plateaus came from the evolution in the transverse direction.
Okay, I'm not coupling with different bands. No,
no, but
okay.
They come from the spatial structure of the wave function.
Okay.
For this state, you have this series of plateaus.
Okay.
Frequency.
Okay, thank you. More common questions? Okay, maybe we can wait 2 or 3 minutes, or if anyone has a question, please put it in the chat or tell me, I will unmute you.
Perhaps
yes, Matthew, yes, Matthew, please go ahead with your question. Yeah. Sorry, I cannot unmute. What's happening? Oh, the question is.
Yes.
Sorry.
Sorry. Yeah. So I was wondering, these 10 states that you've chosen in the left figure, why they are not chosen symmetrically around the k=0 point. Also, when you chose 4 states, you chose to put them on the right side instead of choosing them symmetrically. Why is this?
Okay, just to not repeat this state 2 times. because this is exactly the same point.
Yes, yes, all right. Okay, I see. Thanks.
Yes, Fernando, you wanted to say something?
No, just to note that I think it would be better to wait until 11:30 to stay within the schedule.
Yeah, sure.
Sure.
We can make a 5 minutes break.
If there are no questions, maybe we can stop the recording, but it's up to you. Anyway, you can wait and maybe someone raises a question. Meanwhile, whatever.
Yes, maybe I can ask one also. What do you expect if you do 2D simulation, for example? If you put what do you expect? I mean, to see.
Sorry, can you repeat?
What do you expect to see if you do a 2D grid, for example?
In the okay.
I mean, the spectrum. So you expect to see something similar, or
yes, depending on the spatial frequencies of the wave function in the 2D system, we expect to have a similar situation, because this is like in the light case, when you have a one-dimensional or two-dimensional diffraction mass, you recover the initial shape in one dimension or in 2 dimensions, depending on the initial distribution.
Okay. Thank you very much. Okay, let's wait 5 minutes and we continue with the other talks.
Can I make just a historical question on how all this Talbot effect started? It was discovered in the 19th century. In which context? Because there were not. It was discovered in the context of optics, or?
Yes, in the context of optics. Was Talbot who did the first experiment where he observed this effect in the near field of diffraction with light.
From Sahra Norvac. Please, Sahra, share your screen and your talk. And the talk is about ab initio study of high-order harmonics and isolated attosecond pulses from a solid target. Thank you very much. Sorry, we couldn't hear you. Oh.
Okay.
Oh, yeah. No, it's better.
Okay. Hello everyone, welcome to my talk. I'm Zahra Nurbakhsh, postdoc researcher from Max Planck Institute in Hamburg, from Professor Angel Rubio's group. As we see, this is a theoretical study, and the focus of my presentation is to generating isolated attosecond pulses actually find a situation to generate isolated attosecond pulses from a solid target. In this regard, using two color pulses, we produce asymmetric pulses which combine which localize the pulse energy in a shorter area of its duration. Actually, the first color is fixed here, which is our fundamental pulse, but the second for pulse frequency, strength, and intensity and phase difference of as well as its direction. These are the parameters which are tuned to find the desirable high harmonics and isolated attosecond pulse. Besides the pulse properties, actually the target system is very important. For this, we consider MgO crystal, which is a well-known system in HSG community. MgO is a ionic crystal with a wide band gap, and because of its ionic behavior, it also has the advantage of atomic system, advantage of both crystal and atomic system in one material. We also consider the anisotropic behavior in MgO crystal in high harmonics emission, and the light matter interaction are simulated by ab initio time dependent density functional theory which is implemented in Octopus code by self-consistent solution of the Conduction equation gives us the time-dependent density, which the time derivative of density give us the electron current, and the electron current could give us the high harmonics spectra, and finally by considering an appropriate energy window, we could find the isolated attosecond pulse from harmonics emission, which is in the isolated attosecond pulse is important to study the electron motion in molecule or condensed matter systems. In addition, using two color, by rotating the second color polarization direction, we shows the possibility of having an elliptical isolated attosecond pulse, which is important to study the electron motion in a spin polarized system. Okay, let me start by one color pulse HSG. Here I will summarize of the fundamental pulse properties, which has the wavelength of 1.8 micron, the electric field of 0.6 volt over angstrom. The pulse duration is 18 femtosecond, and it is the pulse polarization is along the 100 direction of MgO crystal. The harmonics, the HSG spectrum is here. As you see, the high harmonics up to number 30 are generated actually because of the time reversal symmetry in MgO crystal. The even harmonics are absent, but the odd harmonics up to cutoff energy of 22 electron volts are generated. In solids, the high harmonics generation are usually explained by interband and intraband contribution. For the first four harmonics here, where their energies are below the band gap, they are arised by intraband dynamics, but for the higher energies, both interband and intraband are contributed, and as a result of that, here we see a noisier signals. The time frequency analysis, which shows here, indicate that no isolated attosecond pulse could be resulted from this spectrum. And as you see here, actually we have a train of attosecond pulses. Also here the time-dependent vector potential as well as the time-dependent electric field are shown here. And yes, the HHG has its maximum for energy range between about 15 to 20 electron volt. As you can see here, this harmonic emission shows a sheep, actually auto sheep with positive sign. Let's move to the two color pulses. Yes, here the second color direction, shape, and duration is same as the first color, same as all fundamental pulse, but the second color strength, frequency, and phase difference are tuned to find the desirable properties. Actually, the HHGS, the pulse shape, as well as the HHG spectra of engineering with these parameters. Yes, as these time frequency analyses show, in all cases, we can define an appropriate energy window to extract isolated attosecond pulses, as reported here. Of isolated attosecond pulses, which have the duration about 2 to 300 attosecond, has much shorter time duration than what reported in MOS2, which is about 2000 attosecond, or what measured experimentally in silicon oxide, which is about 500 attosecond. In addition, the energy window which we found here in MGO is much wider than what measured in silicon oxide, which is just 10 electron volt, or what calculated in molybdenum disulfide, which is very short. For example, here our bandwidth is from about 17 electron volt up to the cutoff, HHG cutoff energy, which is about 45 electron volt. Okay. And again, an auto ship appears here for the energy range, same as the previous one, but here our ship shows the negative sign, which shows the complex dynamics of electron in MGO bands. Here I show the I show the HHG spectra of the two color pulses, which I show you in the previous slide. As you see, the electric field increases from right to left. As a result of that, you can see the cutoff energy increases. The cutoff energy is shown by the gray dashed line here. But this enhancement, this dependence is not linearly. Also, as you, let me, okay. Also, as you can see here, as a result of the electric field enhancement, here the pulse, here the brightness of our isolated attosecond pulses increases from right to left, but there is no serious dependence between the duration of our isolated attosecond pulses and pulse intensity. In the right, I show the high harmonics spectra for one color pulses. The pulse properties here is same as the fundamental pulse, but its density, its intensity or the electric field increases from right to left. As a result of that, the cutoff energy increases, but now we can we can see the linear enhancement of cutoff energy for one color pulses. Also, the asymmetric two color pulses show shorter cutoff energy in comparison with the one colors. As you see in the previous slide, no isolated attosecond pulse was extracted from our fundamental pulse, but as you can see here, by increasing the pulse intensity, now we can find, we can extract some isolated attosecond pulses. This result is almost opposite to what we see from two color pulses, which the isolated attosecond pulse duration was almost independent from pulse intensity, which shows the importance of asymmetric pulses in isolated attosecond pulse generation.
You have 2 minutes left.
Okay. Also, the isolated attosecond pulse duration for the two color pulses are much shorter than the isolated attosecond pulse duration for single color pulse, as well as the bandwidth, which is much wider than the bandwidth here. Another worth mentioned point which we can see here is the time that the isolated attosecond pulse extracted regarding to the electric field and vector potential externum. For example, in the red sign, the isolated attosecond pulse extract in the electric field externum, while in the blue signs it extracted in the vector potential externum or electric field zeros of electric field. It comes from the actually different mechanism of emitting harmonics in each isolated attosecond pulse. For example, when the electric field enhances, it increases the band structure curvature, and as a result of that, intraband dynamic increases. But when the vector potential increases, the band gap increases as a result of that. The interband contribution increases. Let's move to, I want to show here the HSG response to anisotropy in MgO crystal. Now we have a 2-color laser pulse, and here the figures show the HSG resulting from the same input pulse, but in different polarization direction. And as you can see here, the HSG resulting from the pulse polarization in 100 direction is much higher than the HSG in 110 or 111 direction, which can be explained by the strong ionic potential in this direction, as the nuclei potential can be affect the high harmonics emission by this equation. The impact of nuclei potential gradient can be explained by this equation. And in this direction, we have all the ionic potential shows a stronger gradient, so we have a stronger HSG in this direction. Also, the isolated attosecond pulse is much shorter than other direction, and also much brighter. Its brightness is higher than other directions. The auto sheet with positive and negative sign can be seen here, which shows the complex dynamics of electron motion in MgO bands. Let's move to the nonlinear pulse, and now our second pulse polarization, actually our first pulse is fixed and is along 100 direction, but our second color rotate from X direction to Y direction. And as the polar HSG diagram shows here, as a result of this rotation, the high harmonics fall off continuously, and also the cutoff energy decreases. The cutoff energy for non-rotated case is 36 electron volt, and it decreases to 25 electron volt. Here I show the isolated attosecond pulse, which can be extracted from the non-rotated case here, and for theta equal to 45 degree, as you can see, by appropriately tuning the input parameters, we can have an elliptical isolated attosecond pulses. Here the X polarized and Y polarized pulses are emitted in the same time. The elliptical isolated attosecond pulses are important to study a spin polarized system. Let me summarize my main results using on the basis of ab initio time-dependent and functional theory. We show extracting isolated attosecond pulse with duration of 200 to 300 attoseconds. We study the anisotropic behavior of MG or crystal, and we show the linear dependence of cutoff energy to electric field, and we show appearance of auto shift for energies between 15 to 20 electron volt, which at this energy range, the band structure, MGO band structure, show line conduction bands, and also we shows the possibility of having elliptical isolated attosecond pulse, which is not produced in traditional atomic and gaseous systems. Of results is not published yet, but hopefully in the next few days it will be available in archive. Okay, thank you very much for your attention.
Thank you very much for the very complete talk. So we have time for only one short question. Someone wants to try? Okay, so yes, please, Francisco, go ahead. Yeah. I think you should mute yourself because I cannot do it.
Okay.
Sorry, Mariela, I cannot unmute the people. I don't know what happened.
Okay, I think now, I thank you for the nice talk. I just wanted to ask, in slide 5, you showed that you found an effect on the anisotropy of the pulse. How do you quantify the anisotropy of the pulse, or how did you perform that comparison on the effect of the anisotropy of the pulse?
Okay, as I told, all these diagrams resulted from same pulse, but in different direction. So the difference
I think it was slide number 5, I think it was, because this is anisotropy of the material,
no,
right?
here we don't, I don't speak about anisotropy. I show anisotropy here.
No, but in slide number 5, you mentioned there the importance of asymmetric pulse in the production of the attosecond pulses, right?
Yeah.
That's what and so how do you quantify the anisotropy? What's your definition, or how do you perform that study of the anisotropy of the pulse?
Okay, as you see, for two color pulses, all two color pulses are asymmetric, and as you see, the asymmetric pulses gives us much shorter isolated attosecond pulses. I don't understand your question. I think I don't speak about anisotropy here. I speak about
asymmetry. Sorry, the asymmetry,
no,
the asymmetry of the pulse. Yes,
yes. Using the symmetric pulse, we can actually localize the pulse energy in a shorter area of the pulse, and so it could gives us much tinier isolated attosecond pulses.
No, okay.
I hope I could answer your question.
Yeah, no, the question was just because there could be an effect of the intensity of the second pulse or the time delay. And so sometimes in some studies about the asymmetry of the pulse, there are different definitions for the asymmetry of the pulse. Sometimes it's the ratio between the positive and negative parts of the pulse, or I don't know. So I just wanted to know how did you define the asymmetry for your pulse? That's what was the question, but.
As the electric field was shown here, you can see here we don't have symmetric pulse like this, and actually the second pulse destroyed the pulse symmetry.
Yeah, but you could have a symmetric pulse, two-color pulse. So it's not like you will always obtain an asymmetric pulse because of the from a two-color pulse, right? You can have a two-color asymmetric pulse or a two-color symmetric pulse. That was my.
Because of the phase difference, also it's not symmetric, and now our pulse is asymmetric.
Okay.
Thank you very much for the question. Yeah, please, yes, we are going to the last talk. Sorry for the small delay. Please, Oscar Surron Cifuentes is going to talk about mechanism for high-order harmonic generation in graphene and carbon nanotubes. Please, the floor is yours. Yeah. Sorry, I cannot unmute the speaker. I think you should unmute yourself. Yeah, now it's okay. Thank you.
Hello, do you hear me?
Yes, perfect, yes. Thank you.
The video?
Yes, everything is perfect, yeah.
Okay, sorry about. Okay,
no.
So let's go. First, let me thank the organizers for the opportunity of giving this talk that has been prepared in conjunction with colleagues from the Universidad de Salamanca and the Universidad Autónoma de Madrid. The presentation will address our recent work on the mechanism for high harmonic generation in graphene and carbon nanotubes. Our model for graphene is based on the well-known tight banding description within the nearest neighbors approximation. I would just like to remark again that the electronic bands of graphene are degenerated at the Dirac points, and this topological feature of the band structure will play a fundamental role in high harmonic generation, as we shall see later. In the model, we write the wave function of the Bloch electron as a little is also shown as a shaded area, the pink shaded area in the background of the figure, which is dominated by the Van Hoff singularities corresponding to the points where the slope of the bands is null. So the interaction with the field, with the laser pulse, is given by this term in the dipole approximation, where F is stands for the electric field and QG is the elementary charge. Then the time-dependent Schrödinger equation leads to a system which corresponds to a two-level parametric oscillator where the parameter T is included in the equations through the kinetic quasimomentum kappa. Note that the field interacts through the matrix element D, the Berry connection, which diverges at the Dirac points. This fact introduces extra complexity in the integration of the equations due to the numerical instabilities that appear as a consequence of such divergence. Nevertheless, this problem can be circumvented with an appropriate change of basis in such a way that D is completely removed from the equations. These are the equations that we are solving without any further approximation. These dynamical equations have been integrated considering infrared driving pulses with a beam aimed perpendicularly to the target. The videos show the occupation density in the conduction band for a driving field in a near-infrared regime at two different intensities. In these simulations, the electric field is assumed linearly polarized along the vertical direction, along the y direction. Note that the population concentrates in regions near the Dirac points, creating interference fringes along the polarization direction, which grow as the pulse evolves in time. That is, the population is promoted to the conduction band near the Dirac points and then expanded to the rest of the band, quivering along the polarization direction of the field. Once we have the probability coefficients, we can calculate the emission dipole and the spectrum through Fourier transform. The spectrum in panel A shows the characteristic features of high harmonic generation phenomena with a clear emergence of a non-perturbative spectral plateau extending up to a certain maximum cutoff frequency. We have also used polarized laser drivers in our simulations with agreement with recent experimental results. For example, you can check these two references where the harmonic yield is analyzed versus the polarization of the input field. But remarkably, our simulation shows that unlike other physical systems, the cutoff scaling saturates at the largest intensities, and it is not described by any simple law, linear or quadratic, as you can see in these panels. In these figures, the pink color area stands for intensities above the damage threshold. We can see that the saturated cutoff can be reached below the threshold damage in the mid-infrared regime. And it's also remarkable that in all cases, the saturated cutoff corresponds to a photon energy of 17.8 electron volts, which is the maximum band gap at the viewing zone. Therefore, there are three main conclusions that can be drawn from the high harmonic spectra from graphene. The first one is that we see the emergence of the spectral plateau at large intensities. The second, that there is a non-trivial cutoff dependence with the intensity. And third, that there is a limiting photon energy close to the maximum band gap of the material. The interpretation of these conclusions will allow us to unveil the fundamental mechanism for high harmonic generation in graphene. A similar pattern is obtained upon irradiation of carbon nanotubes with a cutoff scaling non-trivial that also saturate at the largest intensities. This result allows us to make a similar treatment of high harmonic generation both in graphene and in carbon nanotubes. But there is an interesting difference with graphene. In panel A, I show the magnitude of the Berry connection between the conduction and valence bands. Note that the matrix element is null for the band crossing at the Dirac point. Thereby, no excitation occurs at this point, and the contribution of this band to the total high harmonic spectra corresponds solely to intraband dynamics. For the rest of the bands, the matrix element shows peaks of magnitude which increase with m. The absolute is reached at the first Van Hoff singularity, as you can see here. This fact suggests that the interaction with the driving laser is much stronger for the states packed at the first Van Hoff singularity than for others, and therefore that the interband emission spectra is mainly due to transition within such states. Panel B shows the harmonic yield from 99 ampere. The dot lines indicates the intraband spectral component. Note that the main contribution for the higher harmonics is the interband component. If we analyze the contribution of the different parts of the different bands to the emission spectra for the same tube, we obtain this panel over here. So that the total emission plotted in solid red in here is the coherent addition of the contributions from all those bands. Note that the higher order harmonics are given by the contribution only from the band m = 8. If you see here the green solid line and compare with the red solid line here, you will see that the high harmonic spectrum, in this case, all the harmonic except the third, is explained just by the band m = 8, which is connected with the first Van Hove singularity. The other points of the viewing zone, where the Berry connection and the curvature of the bands is weaker, contribute to the lower harmonics, mainly with intraband radiation. I then pass to discuss the model for high harmonic emission that yields from these results. To explain the emission mechanism, we first write the general solution of the time-dependent Röntgen equation in integral form. And now, due to the singular behavior of the matrix element at the vicinity of the Dirac points or the first Van Hove singularities in the case of nanotubes, we consider D as an impulse function. This answer let us write the probability coefficients in a much simpler form. And the interpretation of these expressions is straightforward. When the interaction begins, the electron starts quivering the valence band, following the trajectory defined by the kinetic quasi-momentum. Eventually, the electron reaches the Dirac point and is promoted to the conduction band, leaving a hole. Note that there is no tunnel excitation. The promotion to the conduction band is caused by the non-adiabatic crossing through the Dirac point. Once the electron-hole pair is created, the electron keeps quivering in the conduction band while the hole oscillates in the valence band following the trajectory given by kappa. In the case of carbon nanotubes, the promotion to the conduction band follows a similar pattern, but in this case, the process is connected to the non-adiabatic crossing through the fifth Van Hove singularity. So here is the central point of my presentation. The main idea is that the promotion to the conduction band in these low-dimensional systems is made without tunnel excitation. To explain the harmonic emission, we have developed a semi-classical model based on the saddle point approach, which concludes that the harmonic emission takes place at instant t when the trajectories of the electron and the hole overlap in direct space, emitting a photon which is resonant with the bandgap at that instant of time. This semi-classical model is better understood by means of the following map. In the horizontal axis, we plot the time when the electron-hole pair is created in units of the laser period. And in the vertical axis, we indicate the time t when the electron and the hole recombine. The contours show the bandgap in laser frequency units, which corresponds to the energy of the emitted photon. Note that not all the energy values are allowed because there is another condition that has to be fulfilled, is that the semi-classical trajectories of the electron and the hole have to overlap in direct space. To illustrate this idea, we can use the figures on the right side of the slides, which show two complementary cases. The black lines here and here represent the trajectories of the electron and the hole during the excursion. So once the pair is created, the electron and the hole follow their particular trajectories, and they will recombine and emit a photon resonant with the bandgap if their trajectories overlap at some time t in direct space. This happens in panel A, as you can see, but not in panel B, because in this case, in panel B, the electron and the hole are spatially apart at the expected recombination time. Thus, according to this model, the cutoff frequency is given by the maximum energy contour in the map that lies on the red area. So only those points, those pairs for the generation time and the recombination time that lie on the red area of the map mean that the photon will be emitted. In all cases, the cutoff saturation energy corresponds to the maximum interband gap between the electron and the hole during the oscillation in the reciprocal space. If we increase the intensity, we see that the topology of the red color area in the map becomes much more complex. And it is interesting to note that the same harmonic could be emitted by two or more semiclassical trajectories within the same half cycle of the field. As a result, the high harmonic spectra from these low dimensional carbon allotropes are more intricate, not as regular as in atoms or molecules. Finally, as we can see here, the cutoff prediction given by the semiclassical model, which is expressed by the red circles, is in excellent agreement with the results of the numerical integration of the time-dependent Schrödinger equations, which are represented by the blue diagrams. To wrap up, we can enumerate the main conclusion of this presentation. Our results show that the emergence of a non-perturbative spectral plateau at large intensities, but unlike other physical systems, we find that there is no simple law governing the scaling of the cutoff frequency. Using a saddle point approximation model for the emission dipole, we show that the first step for high harmonic generation, both in graphene and in carbon nanotubes, is radically different from the channeling the ionization excitation process found in atoms, molecules, and finite gap materials. And it is closely related to the topological features of the electronic band structure. According to the semiclassical model, the emission of the photon occurs when the semiclassical trajectories of the electron and the hole overlap in direct space. The cutoff prediction yielded from this semiclassical model is in excellent agreement with the results obtained integrating the time-dependent Schrödinger equation. So thank you very much, and now I will be open for your questions, if any.
Thank you, Oscar, for the very nice talk. Please, we have 5 minutes for questions. If everyone wants to ask something. So I have a question related to the intensity. So what is the maximum? You use 10 to 13, but are you reaching some damage threshold already, or?
Well,
or is theoretical only? Yeah. What is the limitation of your model?
The limitation will depend in the wavelength, of course. So
okay.
So depending on the wavelength,
so you can
scale is obtaining at lower or larger intensities. So what we can see for that is that the high harmonic emission is optimized in the mid-infrared regime, as you can see here.
Yeah, exactly. Okay.
Because if you are in the near infrared,
you can
the threshold without reaching the maximum cutoff.
Okay. Okay. Thank you. More common questions? So if not, I would like to close the session and thank all the speakers, and particularly our Zoom genius, Mariela and Pablo Molina, who have helped us a lot with this setup and setting everything. And probably Fernando wants to say something?
No, just to thank everybody. So Dieter is also here.